Water is blue. Even the water in the drinking glass next to you. It's not just oceans and glaciers. So why does only some water look blue? If you're like us, you were told as a kid that water is blue because the sky is blue. The water reflects the sky's color, which makes us perceive it to have the same, or at least a similar color. This makes sense, but is only a part of why water outside is blue, when really, all water is blue, and that explanation does not account for this fact. Before we go further, here's a quick refresher on color. Color, as we know it, corresponds to different wavelengths of light included in the visible spectrum, that is, the range of wavelengths humans can see. Objects absorb different wavelengths of light in different quantities. The part that we see is what remains when amounts of wavelengths are removed. Water, like every object, absorbs some amount of almost all wavelengths of light. However, it absorbs a lot of red and not a lot of blue. The combination of wavelengths remaining form the color blue. This is why water is blue. This is an important foundation, but it alone doesn't explain why water is specifically blue of all colors, or why your glass of water doesn't look like any color at all. Let's tackle the first point by going to a microscopic point of view. Why is water specifically blue? As we know, water is the molecule H2O. 2 hydrogen atoms each covalently single bonded to 1 oxygen atom. The covalent bonds act like springs connecting the atoms. They are free to stretch, bend, rock, wag, and twist. This is known as molecular vibration. The frequency of the molecular vibration depends on the mass of the atoms and the strength of the covalent bond connecting them, which is very intuitive. A light ray travels through an object until it comes into contact with a molecule. When this happens, the light provides some of its energy to the molecule to begin vibrating. Different wavelengths of light have different energies. Some energies are just right for a certain type of molecular vibration to occur, so they get absorbed most, but almost every wavelength gets absorbed at least a little. The mass of the atoms and the strength of the covalent bonds connecting them in water just so happens to cause the molecules to stretch and bend a lot when absorbing wavelengths associated with the color red. This is why we see water as the color blue. So why doesn't your glass of water look blue then? Let's mix in a macroscopic point of view. The question here is actually, what determines how blue something is? The thicker an object is, the further the distance light has to travel through it. This distance is called the path length of the light. A larger path length means that there are more opportunities for light to hit the molecules of an object, since it is passing through more of them. The more collisions that occur, the more red light is absorbed, yielding a more visible blue. This is why large objects, like oceans and glaciers, appear more blue than your glass of water. Light has a much larger path length through the ocean than the minuscule size of your cup. Naturally, the largest bodies of water are outside, under the sky. This is the cause of the confusion. Sure, they do reflect part of the sky's blue color, but this has nothing to do with all water being blue. It really comes down to just 3 key points. 1. Water mostly absorbs the red wavelengths of light because of its molecular properties. 2. We see the absence of the color red as blue. And 3. Larger bodies of water absorb more red wavelengths as light traveling through them has a larger path length. This also explains why the bottom of the ocean is so dark. The light had so many molecules to pass through, so many opportunities for collision, that most of it did not make it to the bottom. There is a lot to learn from water being blue.